from 7.1, what if you recall, the function that we begin with is the function of t, and we use the Laplace transform applied to the function of the t and becomes the function of the s. So changing from the t variable to the s variable. So the first part of 7.3, we will talk about translation on the s-axis. That is the axis of the Laplace transform. And then the second part is the translation on the t-axis, which is the translation of the axis of the original function before we apply the Laplace transform. And that part, it has the unit step function involved. Okay, so by definition of the Laplace transform in 7.1, the Laplace of the function f of t is the improper integral from 0 to infinity of the kernel e to the negative st multiplied by the function f with respect to t. So that's the piece that you multiply to the function and form the integrand of the improper integral. But now we are talking about the translation on the s-axis. So we're going to work on the Laplace transform of the function that has e to the power at multiplied to the original function. So with this product, the e to the at times e to the at and the f of t, and the Laplace of this product is the Laplace of the translation s to s minus a. And we can rewrite this as the Laplace of the function, and translation like is supposed to be the variable s, but now we're going to use the s minus a, like translate from the point origin to the point s equals a. And the example that I mentioned earlier, like y equals, if we have y equals x squared, we have the graph, the parabola graph, like we always, we use all the time. If you have x minus 1 squared, so that means the origin or the vertex of the parabola will be shifted or translated to the right 1 unit. And similar way, and this one, it affect to the original function by shifting to the right by a unit. The absolute value, which means we use the absolute value to represent the quantity or the distance that away from the origin point. Okay, so this is the first translation theorem. They have the Laplace of e to the at times st is the Laplace of the s minus a, or the f of s minus a. Okay, so what we have to do, if you have the form of the function as the e to the power multiplied by the function, so we can identify, like the first example, we're gonna treat it like, as we see this as the Laplace of the e to the power at multiplied by the function of the t. When you see this pattern, you can see this as the a for this problem is 5, and the function ft is t to the third power. Okay, once you see this, and you're going to apply the first translation theorem, which means it's the same as the Laplace of the function of the t, but we're going to shift the s to the s minus a, and this case going to be the s minus 5. So the Laplace of the f of t, which is the Laplace of t to the third power, whatever we have, we're going to translate s to s minus 5. Okay, this is the first translation theorem. So then what we have to work on, we work on the Laplace of t to the power 3 from the theorem in 7.1. So I put on the side here as the list of the theorem or the formulas that we can apply to different form of the functions. So for the Laplace of the polynomial t to the power n, in this case, n is 3. So we use the formula like n factorial. So this is going to be n factorial, or let me write n as the value 5. So going to be no, n is 3, sorry. So it'll be 3 factorial divided by s to the power 3 plus 1. But we're going to translate s to s minus 5. So this Laplace becomes 3 factorial is 6 and divided by s minus 5 to the power 4 as the value or the Laplace of e to the 5t times t to the third. Okay, so that's the first problem. And then let's see another example and I'll ask question. The second example, if we write it as a pattern, like the Laplace of e to the at multiplied by the function t. This case, the a is, as you see, a is negative 2, and the function t is the cosine of 4t. Okay, so this Laplace transform, so Laplace of e to the negative 2t cosine of 4t is the Laplace of the function, which is the cosine of the 4t. Whatever that comes out, we're going to translate s to s minus a, which is s minus negative 2. So the Laplace of the cosine kt, as the theorem E there on the right side, the Laplace of cosine kt, s on the top, s as a numerator, and s squared plus k squared. For this problem, the k is 4. Now the Laplace of cosine 4t is going to be s divided by s squared plus 4 squared. And then we're going to shift the s to s plus 2. Okay? Now the final result going to be s plus 2, s replaced by the s plus 2 divided by the quantity s plus 2 squared plus 16. And this is not the final solution. What you have to do, just clean up a little bit on the denominator, like expand the perfect squared. So s plus 2 is s squared plus 4s plus 4, and then plus 16, and combine 4 and 16 to be 20. Now, the final answer will be s plus 2 divided by s squared plus 4s plus 20 as the value of the Laplace e to the negative 2t cosine of 4t. Okay, so that's the answer. So the use of this is when we work on the differential equation, the non-homogeneous, and the external force, or the non-homogeneous function on the right side, the non-zero function. When you apply the Laplace transform, it could be in the form that we are working on that has to, that's required the first translation theorem. And then the second part of solving the differential equation, we're going to do the inverse Laplace transform.